Have you ever stopped to think about how a perfectly clean, crisp digital signal can leave a transmitter, travel through a simple cable, or even just through the air, and show up at the other end as a complete, garbled mess? It's a huge problem in electronics, and the answer isn't in the signal itself, but in the journey it takes. So, how do we fix this? Well, let's dive in.
In this explainer, we're going to crack this case wide open. First, we'll investigate the crime scene, the case of signal degradation. Then, we'll uncover the actual culprit by digging into the physics of an echo. After that, we'll see the full extent of the damage in what's called a cascade of reflections. And finally, we'll lay down the law, the golden rules of design that stop this crime from ever happening again.
All right, let's start by looking at the problem head-on. A perfect signal goes in one end, and a corrupted, ugly version comes out the other. The big question is, why?
Okay, here's the evidence. Look at the left. That is our original signal, a beautiful, clean, perfect series of +5-volt digital pulses. This is exactly what we wanted to send. But look what arrived on the right. It's a distorted, noisy disaster. And get this, it even has a big negative voltage spike. The information we sent is basically gone. So here's our scene of the crime. The signal leaves a power amplifier, travels through some kind of transmission medium, it could be the atmosphere, a cable, anything, and gets picked up by a low noise amplifier. Somewhere in that empty space, our perfect signal got mangled. And this isn't just a textbook problem. This is a battle that happens inside your phone and your Wi-Fi router millions of times a second.
And this all boils down to the one crucial question we have to answer. How do we protect that signal? How do we stop its perfect, precise shape from falling apart as it makes that journey from point A to point B?
To figure that out, we have to get our hands dirty and really dig into the physics of it. We need to understand what's actually going on inside that transmission medium. It's time to find the real culprit behind all this signal destruction.
Our first big clue is a concept called characteristic impedance, or Z0. Now this is super important. This is not a physical resistor that you can see or touch. Think of it more like the density of the air or the thickness of water. It's this invisible, built-in property of the medium itself that tells an electromagnetic wave how to travel through it.
So yeah, you can't just remove Z0. It's a purely mathematical property woven into the very fabric of the medium. It's calculated from things like the inductance and capacitance of a wire. To the wave that's traveling along, the path feels like a resistor of value Z0, even though there's nothing physically there.
So, if the medium has this invisible property, what happens when the signal gets to the end of the road and hits the receiver, or what we call the load? Well, if the load's own impedance doesn't perfectly match the medium's characteristic impedance, it's like a sound wave hitting a wall. Some of the energy gets through, but a chunk of it literally bounces off, creating an echo that starts traveling all the way back to where it came from.
And believe it or not, we can actually put a number on this reflection. The villain of our story has a name. It's the reflection coefficient, and we represent it with the Greek letter gamma. It's a simple little formula that tells us exactly how much of our signal is going to bounce back.
Think of it like a perfectly balanced scale. In an ideal world, the load impedance, ZL, is exactly the same as the medium's impedance, Z0. The scale is perfectly level. Our reflection coefficient, gamma, is 0. This means the boundary is completely invisible to the wave. 100% of the energy gets absorbed. No echoes, perfect signal transfer.
But what if the load is heavier than the medium, meaning ZL is bigger than Z0? Well, the scale tips down. The reflection coefficient becomes a positive number. And what happens? A positive voltage echo, basically a smaller, upright copy of our original wave, bounces right back toward the source.
And on the flip side, what if the load is lighter than the medium? ZL is less than Z0. The scale tips the other way. Now the reflection coefficient is negative. And this is where it gets really weird. This creates a mathematically inverted echo. A negative voltage wave gets reflected back.
So, we know a mismatch creates an echo. Big deal, right? Well, it's a much bigger deal than you might think. Because that first echo is just the beginning. Let's trace what happens to all this trapped energy over time.
Let's walk through a real example to see how this gets out of hand. Imagine a 1-volt source with 100 ohms of its own impedance, trying to send a signal down a 200-ohm medium. The instant it launches, the wave doesn't see the full 1 volt. It sees a voltage divider between the source and the medium, so it only launches 2/3 of a volt. Now that 2/3 volt wave travels to the load. Let's say the load is 100 ohms. That's a light load, right? We just learned that creates a negative reflection. A quick calculation shows us an echo of -2/9 volts starts traveling backwards.
And this is where things go completely off the rails. What you're looking at is a bounce diagram, and it maps the signal's chaotic journey. You see the initial 2/3 V wave travel from left to right. Then you see the -2/9 V echo bounce back. But look what happens when that echo gets back to the source. If the source isn't matched either, it reflects again. The energy gets trapped, fracturing into this infinite series of smaller and smaller echoes, just bouncing back and forth endlessly.
So what does all that bouncing actually look like to the receiver? Check this out. The consequence is devastating. The intended pulse is that clean, perfect 1V square wave we wanted, but the actual received waveform is this ugly staircase. Why? That first little step up is the initial wave arriving. That second step, that's the first echo arriving after it bounced off the source and came back again. Each step after that is another echo showing up, stacking on top of the last one. The original shape is totally gone.
This whole disastrous phenomenon has a name. It's called dispersion. It is the physical warping of our perfect pulse into a degraded mess, all because of the mathematical stacking of those infinite echoes. And here's the bottom line. The reason this is so catastrophic, that distorted shape means a digital 1 might get mistaken for a 0 or a 0 for a 1. The data itself is corrupted and the waveform is lost forever.
Okay, so this seems like a complete nightmare. You might be wondering how any of our technology works at all. Well, this is where the clever engineering comes in. Now we get to the solution. The golden rules of design that engineers use to prevent these reflections from ever happening.
There are two fundamental rules you have to live by. Rule number 1. This is the main goal. Match the load to the medium. Make ZL equal to Z0. You do this, the reflection coefficient is 0, no energy bounces back, and your signal is perfectly preserved. Rule number 2 is your failsafe, your backup plan. If, for some reason, you absolutely cannot match the load, you must match the source to the medium. Why? Because when that first echo comes screaming back, the source acts like a perfect sponge and absorbs it completely, stopping that horrible cascade before it can even start.
And this isn't just theory, this is exactly what engineers do in real-world CMOS RF design. On the transmitter side, the Power Amplifier's internal impedance is painstakingly designed to match the antenna's impedance. That's source matching. On the receiver side, the Low Noise Amplifier's input is tuned to perfectly match that same antenna. That's load matching. They are literally enforcing the golden rules right there in the silicon.
Now, to make sure all these different parts from different companies can actually talk to each other without causing chaos, the industry came up with standards. You've probably seen 50 ohms written on cables and equipment. That's not just some random number. It's a carefully chosen value that gives the best mathematical trade-off between handling high power and not losing too much signal. For things like cable TV, 75 ohms turned out to be the sweet spot for getting minimum loss in those long coaxial cables.
So here's the key takeaway for any designer. Anytime a signal has to leave one chip and travel to another in the outside world, it has to play by the rules. It has to be 50 ohms, period. But, and this is really cool, once the signal is safe inside a single silicon chip, the designer has total freedom. The tiny path between a low noise amplifier and a mixer on the same chip can be whatever impedance they want, as long as they make sure those two internal parts are matched to that new value. So there you have it. The mystery is solved. That pristine signal turns to garbage because of echoes created at mismatched boundaries. And the elegant solution is the art of impedance matching, of making those boundaries invisible. Every single time a signal crosses from one component to another, it has to obey these fundamental rules. It really makes us stop and think, doesn't it? What other invisible laws of physics are all around us, setting the absolute limits of the technology we depend on every single day?